So an IP packet can have a length of up to 64 kilobytes. The IP header is the part that tells us what to do with that IP packet. What's typically contained in the IP payload is a layer 4 packet. And we'll talk about layer 4 in a bit. A lot of this is self-explanatory. The protocol refers to the layer 4 protocol. So that'll be either UDP or TCP. The tricky part is if we fragment. So recall that fragmentation involves splitting a packet up at the data link layer. And so we made the observation that data link layer packets are substantially smaller than layer 3 packets and layer 4 packets. And we said, why? The primary reason is any errors we're going to get are in packet transmission. During the transmission, when that signal is going across the transmission medium, that's where we're going to get errors. Once that packet arrives intact at the receiver, there's generally not very much that's going to happen to it. And that's why we break the data link layers where we're actually transmitting packets. And we break the data link layer packets up into pretty small, 1,500 byte, 2,000 byte chunks to reduce the packet error rate. If I'm sending a 1,000,000 byte packet, I'm going to have a much higher packet error rate than if I'm sending 1,000 byte packets for the same amount of data. It's just that the probability, given the probability of error, the more bytes I send at one time, the more likely it is I have an error. So that's one of the main reasons data link layer packets are smaller than layer 3 packets. The other reason is so people don't get starved out. If you're sending ginormous packets at the media access control layer, then you're hogging up resources and creating long wait times for other people. So data link layer packets are generally much smaller than network layer packets, and so then if we have a large network layer packet, we have to break it up. And there are two ways of breaking it up. One way is we rebuild the packet at each, so the routers are the hop, right? So here's your host. And assume the physical. Now the router really only cares about the network layer. And so for functional purposes, the router doesn't need the transport layer information at all, right? Because the router's job is to get the packet to the destination host. So a router gives you a packet relay service between hosts that are not directly connected, right? Meaning in between them are one or more networks. And for that environment, the data link layer doesn't suffice. That's why we need a network layer. And the network layer achieves that primarily through the function called routing. And so that's why I don't show these are routers, and I don't show the transport layer. And this is a host device because we do have the transport layer. The transport layer finds the application that needs the data. And the analogy I used, I think it's relevant, is you have your house, and that's your IP address. You have the people in your house, those are your applications. They get a transport layer port number. So if 4 people live in your house, they can get mail, then they would have to have their names as part of the address, right? So part of the overall application address is the port number plus the IP address. So IP address gives you the house, the port number gives you the application in the host, and then now you can address everybody. And what in intranet fragmentation, a packet's fragmented and it's rebuilt in every router. The router will rebuild it and refragment it. And that has certain pros and cons, but that's not you just need to know what that is. So intranet fragmentation is where the router will rebuild the packet. It will collect all the fragments up from the input port, rebuild the entire packet, then refragment that packet out the output port. So it comes in as fragments, it's rebuilt, and it's sent out as fragments. Internet doesn't do that. It just forwards the packet, so it does not rebuild the fragments. It just forwards them out as they come in. It still needs a network layer because we still have an IP address and we still have to do routing.
And which one is this you said?
Internet. So at the top we show the TE capitalized in, oh, I can't spell. That's one of my, sorry. It's, so internet fragmentation versus intranet fragmentation. The one we're going to focus on is internet fragmentation because that's what IP does. And so the fields you have to know how to fill out are the ID field. The ID field is same for all the fragments of one original layer 3 packet. So if the layer 3 packet was broken into 10 fragments, then those 10 fragments would have the same ID field. Then you have the D bit and the M bit. The D bit is for do not fragment, so if you set that, there will be no fragmentation. And you will either send it as one packet or you won't send it at all. The M bit is set for more fragments. So if you have 10 fragments, then the first 9 will have the M bit set to 1. The 10th packet will have the M bit set to 0 to indicate that that is the last fragment. And then you have the offset. And that's where you have to know how to calculate something. So we have 8-byte fragments, and you have the maximum length of the packet. And then in the notes we use a different example, but in the class we use Ethernet, which has a 1500 byte maximum packet size. So there are 1500 maximum bytes you could put into an Ethernet packet. And if you divide that by 8, you get 185. And so in every Ethernet packet that's a full size, you have 185 fragments, and that's how you can determine the fragment offset. The first fragment, the first packet, if you have 10 fragments, it's assumed that 9 of them are full, right? Because why would you not fill them up? And the 10th one may or may not be full. So in the first packet, the fragment has to be 0. The fragment offset is 0. So you're starting at the 0th fragment. And then if it's full, it's gonna go to 0 to 184. So in the second packet, the fragment offset will be 185. And then by similar reasoning, in the third packet, the fragment would be 185 plus 185, which is 370, right? So it increments by the number of fragments that are in the packet, yes?
When I did that 1500 divided by 8, I got 187.5.
1500 divided by 8, really? 1500.
It was 1480 we used.
Oh,
14 is the 2.
thank you, I forgot. Thank you, yep. Okay, my bad, you're right, thank you so much.
20 bytes.
So, we have to have the 20, this is where I get, so we have to have the 20 byte header has to be in every fragment. If you didn't put the header in the fragment, the router wouldn't know what to do with the packet, because the router needs the IP address. And the router also needs to rebuild the packet, it needs all that fragmentation information. So it needs the ID, it needs the more bit, it needs the fragment offset. So the 20 byte header goes in every fragment. Yes?
Why did you divide by 8?
Because fragments are defined as being 8 bits long. It's just a definition. So we take out 1500 divided by 20 and you get 1480. And then now you divide that by 8 and that will be 185. You guys can check my math. But thank you for, I don't know why I forgot that.
I
Thank you.
remember the header as soon as you said
Yeah.
it, but I was like, wait a second, that's not 885.
Yeah, because the header has, so So don't make my mistake, put the header in every fragment, right? If you think about it, it's necessary. In the original IP packet, there's only one header. If you have 10 fragments, you're gonna send 10 headers, but you have to, because the information in the header is needed by the router.
So if you tell us that there is something that's 1500,
Well, the
Where-
Ethernet, the reason it's 1500 is because that's the maximum payload of an Ethernet packet.
then we have to assume that the data is part of that 1500 always. Or like any other number that you give us, you always assume the data is a 20-bit header, or not data, the 20-bit header is part of it.
Yes. So if this is an Ethernet packet, and here's my header, and here's my trailer, and here's 1500 bytes, 20 of it has to be the header. Has to be the IP header. So this is my payload section. So this is that's for my payload. And I have 1500 bytes there. And 20 bytes is reserved for the IP header, which leaves me with 1480 bytes, which breaks down into 185 fragments per packet. So in the first packet, this fragment offset, so now we're going back to the IP header. So now in the IP header, we have the ID field is the same for every fragment. So the M is equal to 1 except for the last fragment. The ID is the same for every fragment. And then the offset increments, in the case of Ethernet, the offset would increment by 185. So the first packet, the offset would be 0, because the offset is in terms of fragment offset. So it's 0, then 185, then 370, and the fragment offset will be multiples of this value. And I think that's it. Right, and so then the last thing you have is TTL. So time to live is a value set at the source, and time to live is there to get rid of looping packets. The time to live is also then passed down to the fragments, because the header's passed down to the fragments. And time to live is decremented in each hop. If a packet starts to loop, time to live, TTL will reach 0, and then that fragment is discarded. Now in internet fragmentation, the routers can only discard fragments, they can't discard the whole packet. So if the last fragment, if fragment 10 out of your 10 reaches 0, you would throw that out, but the other 9 got sent, even though that packet's dead. If one fragment reaches TTL is equal to 0, all the fragments are dead on arrival, because you won't be able to rebuild the packet. So one of the downsides of internet fragmentation is that the routers can only abort the fragment. In intranet fragmentation, since the routers rebuild the packet, then you can discard the whole packet. The only entity that can abort the packet in internet fragmentation is the receiving host. And so TTL is the other. So the values you need for fragmentation are the identification, the M bit. D will be set to 0 because you're fragmenting. M will be set to 1 except for the last fragment. You have the identifier that's common to all the fragments, and then you have the fragment offset, which increments based on the number of fragments per maximum packet size. Then if the last packet is not all the way full, that's okay. And that's fragmentation. And now we get into routing. So the first level of routing is the address resolution protocol. And that takes place in the context of a data link layer. And so we have some host devices, let's assume it's a switch, gosh, a linear switch. And then we have a subnet router or gateway router. And if this device is sending an IP packet, so you have IP, source and destination, realize that that packet has to go into a data link layer with a MAC source and destination. And the assumption is you know the destination IP. Pragmatically, if you don't know the destination IP, then you would use a domain name server. Domain name servers, there's several of them in every network, and you would go to the nearest one, and that's a server. So that's not a data mover, so we didn't really talk about that. It provides a service. And the service it provides is it links a bunch of domain names to IP addresses. And so, for example, U of M Dearborn, you would get the network ID for U of M Dearborn. And you get the IP address of the main router for U of M Dearborn. So if you know the domain, but you don't know the IP address, you could use something like a domain name server. That's not really covered in this class, so I'm not really going to ask you that. So the assumption is we know the destination IP, but you might ask, well, how do I know the destination IP? But you've got to you've got to put that IP packet into a data link layer packet, and hence you need to know the MAC destination address. And how would you know that? And we use address resolution protocol. So what ARP does is for each device, it creates a table of MAC and IP address. And it creates a mapping. So if this is A, B, C, and D, and then MAC address alpha, beta, gamma, delta, then you would have alpha, beta, gamma, delta, A, B, C, D, and then you would maintain that table, and when you had to send a packet out, you would look up the packet that you need, or I'm sorry, you would look up the MAC address, and then now you can properly build your data link layer packet because you know the destination MAC is here. If the address you're trying to go to is not in your ARP table, then you would send out an ARP request. An ARP request is a special packet that goes out, and it has the form, it has the data link, it has to be a data link layer packet, right? So it has to have the MAC source and destination, and then it's an IP packet, so you have to have the IP source and destination, and then in here is the format for an ARP request. And in it is the MAC, is part of the payload, is the MAC source. This is payload. It's not, this is used for actually addressing. It has the MAC source and destination, the IP source and destination, and then this field is blank. The destination MAC is blank. And then you would, there's two ways you can do it. You could send this to your subnet router, and your subnet router will then either have that, it may have a more up-to-date table, or the subnet router will send it out on your behalf, or you could broadcast it. You could put an FF in this field and broadcast it across your subnet. And then in either case, when the IP address of the host that you're targeting receives that, it will send an ARP reply. And the ARP reply will have this destination address filled in, and now you're able to complete your data link layer packet, and then you would update your ARP table. Anytime a device enters the LAN, this happens in Wi-Fi a lot, anytime you enter the LAN, you would do an ARP request reply, that you do an ARP notification that you've entered the network. And the default is every 30 seconds, the router will do a query, and then each device updates its ARP table accordingly. The router is not moving, so the router will have the most up-to-date information. As devices enter or leave, they'll have partial ARP tables. And then, and these build up, you know, when we're talking about it takes time to build up, we're talking a couple seconds, right? It's not like human time, like we're waiting 30 minutes. People will quickly recognize the new device is there. They'll do the ARP request, ARP reply, and then the ARP table will be updated. So the main thing is that the ARP table, what is its purpose? Its purpose is to give you a destination MAC address for any destination IP address, because you have to build the data link layer packet. We're at layer 3, we're doing networking, I have your IP address, but pragmatically I have to put this in a data link layer packet and I need your MAC address. And so the ARP protocol allows me to find your MAC address, the destination MAC addresses, and then each device within the LAN maintains its own ARP table of MAC to IP addresses, and the context is within the LAN. So here, the ARP table on the other side of the subnet router doesn't mean anything, right? Because the MAC addresses are going to be different. That would be a different ARP table, right? So maybe here, there's a router, another subnet router, and some other stuff going on, then they would have to have their own ARP table that applies to this set of directly connected devices. So that is the address resolution protocol, and then it's implemented by sending ARP reply and ARP request packets. If your packet is leaving the network, how would you know that? So if you're in if that's your subnet ID, then your ARP table should have all the entries in that subnet ID, right? And so if you're sending a packet to someone in your own network, then you would insert their MAC destination address by looking up their MAC address. But what if you're going to Amazon, you want to buy something off Amazon? What would you do in that case? What would you do? There you go, right? So how would you know? Well, it's different from here, right? So if it's 141.215, 128, then you know that it's in your subnet, and you should be able to find it, right? And you can send it directly to that device without the intervention of the subnet router. If it's got that same subnet ID, but it's not in your ARP table, then you know your ARP table's out of date, and you need to update your ARP table with an ARP request, ARP reply. But if the IP address is not within your subnet, then you just send it to the router. And then the router will use its routing table and find the next hop. Keep in mind that the MAC address has the context of a local area network. That as you transition, so when your packet starts here, let's say you're at A, you're going to some Z somewhere in the world, and you have this MAC address, and then this would be your subnet router, right? On the next hop, the MAC addresses are going to change. On the next hop, the source would be your subnet router, the destination would be whatever router it's forwarding it to. And in each hop, the MAC addresses are updated, because the MAC addresses are data link layer addresses, and their scope is limited to directly connected devices. Whereas the IP address generally stays the same. Now there are reasons the IP address changes when you're trying to hide your location, but we didn't get into that. For 99% of the routing, the IP addresses stay the same. all right? And then we have rip and distance vector, which we just covered. So distance vector, we have the distance from A to B by C is equal to the cost of A to C plus the minimum distance of C. Wait a minute. Let me do that. Cost of A to C plus the minimum distance of C to B by some, oops, hang on a second. I looked at the clock and now I'm hurrying. The minimum of some W. So what is this saying? This is saying I'm here, I have a neighbor here, my neighbor here has a path to here, and there may be multiple paths, but I'm going to take the minimum path to B. So I'm going from A to B by C. This is this. This is this. And that's distance vector. And there's lots of characteristics of distance vector. I could stay later if you guys want to stay late. I just looked up at the time and it's like I started hurrying. And what happens with distance vector is you initialize and you get to know your neighbors. And your neighbors are initializing at the same time. And then at the next 30-second update, your neighbors will tell you about their neighbors. And at the second 30-second update, they will tell you about their neighbor's neighbors. So now you're 3 hops into the network. And with each update, you go 1 hop deeper into the network. And convergence time is slow, but the amount of overhead is minimal because you're only talking to your neighbor. And if I give you an example of this, it won't go more than a couple, 2, 3 hops. I'm not going to give you a 7-hop example. Take maybe 2 or 3 hops. Because again, if you know how to do 2 or 3, you know how to do them all. It's just giving you a 7-hop problem is error prone. I want you to understand how it works, not if you can be tedious. Actually, good engineering is tedious and methodical. You should develop that habit separately.
How many, for the final, how many questions is it, like the multiple choice, the matching, and then the problem solving?
I gave you a 70-30 split, about as far as I go. Any of you want a copy of the exam today, give me $1,000 check. No, I'm just kidding. No, I haven't written the exam yet, so I don't know. It's a 70-30 split, right? So distance vector, link state. So plan out one distance vector problem of a couple of hops. Plan on something with link state of reasonable. I'm not going to give you this horrible problem that is going to be. I'm going to make it something that can be reasonably solved. Simpler than some of the ones we did in class. Some of the ones we did in class, I was just up here drawing like I think I went 8 to 8, so I had 8 routers for a link state problem. Think maybe 6 at the most. So just understand how to do the link state algorithm. So the difference is in link state, you get all the network information at the first iteration of the network, and there's only one iteration. So distance vector grows update by update, right? Your distance vector table will be updated and mature update by update. In link state, the first thing is to understand the flooding. The rule of the flooding is if you get somebody's link state information you flooded out every port except the one you received it on. And then you can trace that and you can figure out how many link state packets you needed to send. And keep in mind, this is only for one router. Every router does it, right? So for one router, if I have something like this, then if B gets my packet, it didn't receive it on the links to C and D, so it will forward it out C to D, C and D. But don't forget, D's doing the same thing. And C's doing the same thing. All the routers are flooding the information, and then after one network update, you have all the information you need to drive the routing table, which is very different from distance vector. Don't confuse the multiple steps in the link state algorithm with multiple updates in distance vector. Yes, link state has multiple steps, has multiple iterations in the algorithm, but you're not doing network updates. In distance vector, you're solving the distance vector with every update. So in this case, if I'm A, then my information I'm gonna get A to B is 1, I'm gonna get B to C is 5, and I'm gonna get B to D is 10. And now I have all the information I need to generate my routing table, and then the way we did it in class is you started with a set of the source router, and you picked the lowest cost link that you haven't already used. So in this case, I have B to C is 5, B to D is 10, and A to B is 1. So I would pick A to B, and I would add B to my set. So this is called step 0. Step 1, I now have A and B. Here I know that I have A to B is 1. Then I have to say, okay, what new information I have. So now I have so now I have two new informations. I have B to D is 10, B to C is 5, so I take the 5. So now I add C. So the next step, I add C. And I have no new information to add, right? Because C is not connected to anybody. And the next step, I add D. So this is a trivial example. I mean, the one of them would probably be a little harder. But in each step, I pick the lowest cost link available. I add it to my set. I add the new information that I have, and I evaluate it. And I look at any routes I might have. And then I just repeat it. Out of all the information I have now, I pick the next lowest cost route, and I add that to my set. And then I look at the new information I have, and I update any routes I need to update. And then I add the next lowest cost route. And I'm done when all the routers are in my set. And then link state is used in OSPF. OSPF is divided into areas. So in OSPF is a routing protocol that has its own special OSPF packets. So I could have a group of routers here, maybe this is a building, and I could have a group of routers here, maybe this is a building, and maybe I have another group of routers, and this is a building. And then these are areas, and then each of the areas forms their own link state routing, and then I have a backbone that interconnects these areas, and this is a fourth area. So I have individual areas that perform link state routing, then I have a backbone of routers that, and this is within an autonomous system. And then I have a backbone, and the backbone is considered a fourth area. and the backbone routers perform their own link state. Distance vector uses UDP port 520. I'm sorry, RIP. So RIP uses distance vector, that is UDP port 520, and in RIP, the cost is hop count. So each hop is counted as one, and the cost of a route is the number of hops. That's enough, right? So we'll skip some stuff. There's stuff we skipped. There is, but I think